Hey. Okay, so let's go ahead and get moving into this common ion effect. Um, and I'm just sharing my screen. And let's see what, in fact, are we talking about? It should be fairly easy enough for you to understand. So, common ion effect, right? Maybe we'll determine what that effect is by way of solving some problems. I haven't been writing very neatly lately, you guys. It's bothering me. I don't like the way my writing looks. I'm not going to worry about it. It looks fine here, but it looks bad on there. Okay. What is a common ion? Okay. Don't overthink it. It occurs, so let's say that in my coffee cup, I have salt water. Let's say that in this, let's say that we literally have, let's get one that's more insoluble. So let's not have table salt. Let's have something like, here's our compounds, okay? Maybe there's nothing in there, actually. Maybe I do have table salt in here. I have chloride floating around, and I've got barium ions floating around. Okay, now if I was to have another salt that contained barium or chloride, particularly barium because it's more of an insoluble type of ion. So let's say that I have barium carbonate and I want to dissolve it in this solution, or I'm going to add it to this solution, right? It doesn't matter. It would be a solid. We would have a slight bit of dissociation, right? I hope that I didn't write that confusing. And what we have here is a common ion. And the presence of this common ion in the solution prior to me adding and slightly dissociating this compound inhibits the ability for the barium carbonate to dissociate. So the common ion effect occurs under a situation as such, and the presence of this barium ion in the solution, initial presence of barium ion in solution, now listen to it like this, will cause Q to be greater than KSP, and therefore will inhibit the ability, oh man, I'm doing good, of the salt to dissolve. Okay, and produce more ions. There's already too many ions. There's already, okay. I think I was going to say something else and I lost it. It was about to be real good, but okay. I could say as the system will be pushed to the left or reactants. All right, whatever. Hopefully you understand that, all right? Let's do some calculations and see how that works. So we'll obviously look at number one. Given the KSP for silver chloride, AgCl, KSP equals 1.58 times 10 to the negative 10th, right? AgCl will dissociate as such. This will be our solid. Okay. All right, so for the letter A, we need to calculate molar solubility for each one. So in letter A, we're in pure water. Well, what does that tell me? That tells me that I do not have a common ion. Right? Once again, I don't usually put, you can just put SS, right? Or see it. So here I know that if I were to solve for S, I would have my KSP equals S squared, 1.58 times 10 to the negative 10 equals S squared. S equals, oh, I have that right here, you guys. 1.26 times 10 to the negative fifth. Okay, so in pure water, this is the solubility, all right, to the negative 5. That would be moles per liter. Letter B, we're now going to dissolve this in what? I can't see my problem. A solution that has a silver ion concentration, 5.5 to the negative 3. So many emails about late work. All right, that's what this means. So AgCl yields Ag plus Cl. Initially, we have got 5.5 times 10 to the negative third moles per liter of this. This is, this is not present. So we will gain S for C, gain S for chloride, and at equilibrium, we will have 5.5 times 10 to the negative third plus S and S. Okay, now, when we do that, and you will do this, this right here will be so small, right? S will be so small that the term plus S will be negligible. Okay, and I know that because, go up here, I have a KSP that goes to the negative 10. I believe anything lower than a negative 5, a negative 5 is considered negligible. So a negative 10 is considered negligible. Negative 5 and below, negligible. Okay, so what that means is that my KSP, which is equal to the silver concentration, actually I've made a mistake here. So I might as well start over. No, I didn't make a mistake. I didn't make a mistake. I'm sorry. I didn't make a mistake. Is going to be equal to this. I just totally messed myself up. Okay, so KSP, which was what? KSP is 1.58. Get it together, Miss Murphy. People are watching you. So 10 to the negative 10th equals, okay, so we're going to plug, check this out. Hopefully you see it. We're going to plug this in for silver, and we're going to plug this in for chloride, okay? And what we're not going to do is plug the plus S in, and that would make for a much, much harder solution to solve, okay? Okay, so we've got 5.5 times 10 to the negative third. Concentration, and then this is S, okay? And, sorry, let's solve for S. S is going to equal, I have that right here, 2.87 times 10 to the negative 8. Okay? So what do we notice? We notice that when we have the presence of the common ion, silver ion, that we have a decrease in the molar solubility from pure water, where we were at in the negative 5, to the presence of the common ion, we are now in negative 8. All right, letter C. A 0.025 molar potassium chloride solution. 0.025 molar potassium chloride. Well, that dissociates completely because we know that alkali earth metal compounds are fully soluble. So initially, change equilibrium. What that means is initially I have all of this. You should already know this. I will lose all of this and none of it will remain. And I will gain this in a 1-to-1-to-1 relationship. Okay, we are calculating the molar solubility of silver chloride with the presence of a common ion. The common ion this time is the chloride. Okay, so we initially have 0.025 this, none of this, change plus S at equilibrium S 0.25 plus S. We will assume S to be negligible, all right? Because the KSP is so small anyway that this does not proceed very far to the forward direction. So we will not be gaining much. Negligible, all right? And what we have here is our KSP is equal to the silver ion concentration, what we have defined it to be in the chloride ion concentration. KSP, once again, is 1.58 times 10 to the negative 10th. Temperature has not changed. That is equal to S times 0.025. Solve for solubility. That will be our molar solubility of the silver chloride within a solution that has a common ion. Please notice that once again, my solubility is in the -9, whereas in pure water, the solubility was at -5. So the presence of the common ion in the solution minimizes the percent dissociation, because let's look at number 2. Purely in terms of Q and K, no calculations, explain why barium sulfate is less soluble in a solution of sodium sulfate than it is in water. How would we explain that? It said explain using Q and K. Okay, and we need to explain why barium sulfate is less soluble in sodium sulfate than in water. So I need you to do that. All right, what are we going to say? First of all, there is a presence of the common ion. And that common ion will be sulfate. And when this will cause, right, we need Q and K. This will cause Q to be greater than K, right? Because we already have a big number over there. We already have a lot of products over there. Thus, to reach equilibrium, the system will need less ions. I don't like that. I know they want to say something like that. Let's not do that. But greater than the KSP. This will force the EQ position to the reactant side. Right? And that's where the solid is, not where the ions are, not the product side, where the ions are. Okay? I think that's fine. It's kind of weird, but that's kind of a weird question, right? Okay. I believe that's it. And I think I'm right this time, right? Cool. Great, guys. Let's see you soon.